Alright, it's time to finally test this inverter out. And one thing that really strikes me is just how small this is. This is a 1000 watt inverter, and it's only a little bit bigger than some of the 400 watt inverters I've seen, so it's kind of nice that way. It seems pretty solidly built. This is my test setup. Like with other inverters that I've tested, I have two of these deep cycle Autocraft batteries here. They are fully charged, and they are in good condition. This is a 45 amp battery charger that I have connected to them. That makes it a lot like having your car idling and connected to your battery. And I just have their battery clamps that they gave me connected up to the battery. These clamps seem to work really quite well. I like the clamps themselves. The wires I think are a little marginal, so we'll see how hot they get. And then for loads, I have just some resistive loads here, an electric heater. It's got low and high on it. I have some light bulbs down here in this light bar that I made, and I have a fan. So let's turn this inverter on. I already have it all connected up. And the fan inside turns on just briefly and then shuts off. Supposedly it's load controlled, not sure if it's temperature controlled. I would plug my kilowatt meter directly into here, but these outlets are actually upside down. Yeah, I don't know why they chose to put them in that way. It's kind of annoying to me, but maybe they had their reasons. Maybe it's just an assembly convenience. Either way, it's not really all that important. I'm just used to having the outlets the other way. So you can see here that it is outputting about 120 volts. Now I'm going to be doing all my testing with this particular meter. This is not a laboratory piece of equipment. However, I have compared it to calibrated equipment, and it's within about 1%, which is pretty darn good for a consumer grade device. So I'm going to be using this. It's fairly accurate. My inverter is on right now, and I would like to see what the no load current draw from the batteries is, because that was not listed in the specs, and it's pretty important. Looks like it's around 0.8 amps. Yep, 0.8. So this takes 800 milliamps on idle. That's relatively high. I would expect 0.2, 0.3 amps for an inverter like this, so that's not a deal killer, but you certainly would not want to hard connect this up and just let it go. You're going to have to turn on and off when you have loads that turn on and off, because it takes a decent load out of your battery, about 10 watts. Here we are plugged into my multimeter, showing exactly 120 volts. I'll switch it over to the oscilloscope function, and there you can see our really messed up wave. This is a modified sine wave inverter. That's what we would expect. And I am curious what happens to this waveform as I load it down. So I have this electric heater here, and I'm going to plug it in. Let's see what happens to the waveform. The fan in the inverter turned on right away, and you can see that the waveform goes to basically a square wave. Now, this inverter has plenty of input voltage. It's well over 12 volts right now, and it's already a square wave. You can see that the voltage level has not sagged. It's still 120 volts, but my meter is reading 850 watts, and it's already a square wave. If I turn my heater on high, still a square wave. So what this is telling me, and I'll turn it back to off, you can see it goes back to a modified sine wave. This meter doesn't always trigger perfectly, so that's why it's jumping around. You can see that it's a modified sine wave again. So that tells me that this particular inverter has very bad total harmonic distortion. I could hook up a meter to give the total harmonic distortion, but basically assume that this is a square wave inverter once you load it down heavily. Under light loads it seems to work fine. So that means that this won't be particularly good at powering motors and the like. You have an AC unit, this may run it, but it will be less efficient than with a different inverter. This is an advertised 1000 watt power inverter. Let's see what it can really do. They say 1200 watts maximum, 2400 surge. We'll ignore surge for now, but I'm going to turn this electric heater on high and just see what happens. This is a 1500 watt electric heater, and this inverter is actually running it at 1200 watts output. The output voltage has sagged. That's why this 1500 watt heater is only outputting 1100 watts now. But this inverter does appear to be able to do, at least for a short period of time, the 1200 watts that was claimed. And let's really stress this thing. I'm going to turn on some light bulbs and see what happens. And there we go, it just overloaded. So this ran with a 1500 watt heater and 3 100 watt light bulbs before it finally quit operating. And that's pretty impressive for a 1000 watt inverter, an advertised 1000 watt inverter. This thing really can do what's advertised in terms of its maximum output power, 1200 watts. A little bit later we're going to do a continuous load on it, see what gets hot, what doesn't. These cables are already quite warm, so I think I may have to substitute different cables to do that test. But overall, so far the output capabilities of this inverter is looking pretty good. Now, I did mention that the output waveform isn't very good, so let's take a look at this box fan. I'm using this box fan for this because it has a buzzy motor, and you can hear it buzz. And hopefully you can hear about how fast that the fan is running. Now when I turn on this electric heater onto, I'll just turn it on to medium here, low rather, because it has low and high. Hopefully you can hear that the speed of this fan decreases. Well, this heater's too noisy. But the box fan doesn't like the waveform very well because it's not all that clean of a waveform. Now, in its defense, this is a modified sine wave inverter. You don't buy these things for clean waveforms. Some inverters do a much better job than this one does in keeping their waveforms clean. This one had those 200 volt rated capacitors in the output, and this seems to be why, because they don't boost the voltage up high enough to get all that great a waveform. In any case, we're going to ignore the waveform from now on and just concentrate on what it can do. It can do 1200 watts. Let's see what sort of things it can really power now. Let's really stress this thing out. I'm going to run an extension cord to my basement. We'll try some heavy tools that a 1000 watt inverter really wouldn't be expected to run. First up, I'm going to try running my full-sized microwave oven off of this puny little 1000 watt inverter. I have a glass of water in there, and we're just going to let it run for 30 seconds or so. It buzzes horribly. I made a video on this recently, why you should use a sine wave inverter for microwaves in most cases, but you know what? This tiny little 1000 watt inverter does run my full-size microwave. That's pretty cool. Here I am in my basement. I realize the lighting isn't very good, I apologize, but over here I have a number of different appliances that you might want to run off of an inverter. Now, the majority of these really should have a lot bigger inverters than 1000 watts, but I want to see what this thing can really power. After all, I ran my microwave, and that's pretty good. It takes at least a 1500 watt inverter in most cases to run that. So, first of all, I have a circular saw. This is a 13 amp circular saw. You really should have a much bigger inverter for power tools, but let's give it a try. This end is lit, it's plugged into that inverter. We'll plug it into this saw and see if it runs it. So, no, it does not run that saw, nor should it. This really should have a 3000 watt inverter or so to run something like this. Sometimes you can get by on less, but in this case, a 1000 watt inverter can't run this 13 amp power tool. Not much of a surprise. Let's go to another entirely unreasonable appliance. This over here is a 1980s dehumidifier. Now, I've tested the startup surge on this thing. It's about 3,500 watts, a ridiculous amount. But I'm going to plug it in anyway because this usually takes a 3,000 watt inverter to start it, and some 3,000 watt inverters can't even start this thing. So I'm going to plug it in, and let's see what happens. I at least want to know if that inverter goes up in smoke or not. So it gives it a try, it pulses on and off, it doesn't start it. But that also does mean that this inverter has an auto restart. Could be good, could be bad, depending on what you're looking for. I generally like it. So we'll put that aside and move on to something a little bit more reasonable. If you want to vacuum out your car or something, you might want to run a shop vac like this. This is a little 3 horsepower shop vac. Takes a good amount of current, but you might be able to power this off of a 1000 watt inverter. Let's see if this one runs. No issue at all. And fortunately, the motors in these types of appliances don't care if it's sine wave or not. So even though it's a square wave, this thing doesn't care. It runs great. If you want to vacuum out your car, use your shop vac, this thing will probably work for that. That's, again, pretty good for a 1000 watt inverter. This is a household vacuum cleaner. It's a 12 amp vacuum cleaner. And that's a lot more than what you should plug into a inverter like this. That's a 13 amp circular saw that I just tried, so let's see if this runs. So that does not run. Not a huge surprise. But I do have one appliance left here. This is a window air conditioner. Now, a lot of people want to run air conditioners off of their inverters. Now, for appliances like this, you really should have a sine wave inverter. They run a lot more efficiently off of that. They'll take around 30% less electricity, less power out of your batteries, if you use a sine wave inverter. But, you know what? Sine wave inverters cost a lot, right? So maybe you just want to run this temporarily off of a modified sine inverter. Now, this is a 5500 BTU window air conditioner, fairly modern within the last 5 years, but it still has a pretty wicked startup surge, as do all compressors. So I have this thing turned on, and I'm going to plug it into this inverter. If it starts it, I'll be pretty impressed, but let's just see what happens. Alright, let's try that again. I ran an electric heater on this for a little bit, just so that the thermostat now knows that it's warm enough in here to turn on. So let's see if this air conditioner can be powered by that inverter. You can see that it sounds really strange. It does not run evenly at all. And that the power light flickers. I don't know if you can see that on camera, but it's flickering right now. I don't want to burn out my air conditioner, but this inverter does not adequately power this air conditioner. So the inverters seem to power everything you would expect a 1000 watt inverter to power. The air conditioner was a little bit of a disappointment, especially in the way that it didn't power it. The power kind of flickered on and off, and I worried that it could damage the compressor if I left it that way too long. But it did run my microwave oven, which was pretty impressive for a 1000 watt inverter. And you wouldn't really expect a 1000 watt inverter to power an AC unit, so I can't be too disappointed. Next, let's take a look at the overvoltage and undervoltage protections of this particular inverter. I have this inverter hooked up to my variable power supply right here, so I can set the input voltage to whatever I want. It also shows the current that it's drawing. So before I start doing that, let's first take a look at the input no-load power draw. This is with 15 volts input. It takes 0.7 amps out of the battery, or in this case out of the power supply. Let's see what happens as I turn the voltage down. So the input power, no load power draw, does go down. As I turn the input voltage down, which is kind of interesting. Let's see if there's a low voltage alarm on here when I turn this down too far, or if it just shuts off. 10.8, 10.6 volts input, 10.5, and it's still running. and it just shut off. Turn this back up. Looks like you have to power cycle the inverter for it to come back after a... Oh, it just turned back on. So I don't know exactly what the thresholds are. I'll turn this light bulb on here. This is a 15 watt light bulb right over here, just off frame. I'm going to try this one more time, make sure I'm not crazy. Here's 10.5 volts where you'd expect it to shut down. But I can keep going well below 10.5 volts. This light bulb is still on. You can tell that it's getting dimmer. Oh, there it just went. So the low voltage shutdown really is quite a bit lower than 10.5 volts. And I do like that. That means that if you have a battery that isn't in that great a condition or input cables that aren't quite adequate, that it won't shut down too early. The output voltage and output capabilities will sag, no doubt, but there's no low voltage alarm though, which is kind of interesting. So let's check the high voltage shutdown. It turns the fans on, but it doesn't actually turn the inverter off. Oh, there, 16 volts, it just shut off. So it does have a high voltage protection as well. If you turn the voltage up too far, I'm sure it will still get damaged. Those input capacitors are rated for 25 volts. That gives you an idea of what kind of voltage it can tolerate. It does seem to protect itself. And one thing I like seeing is that it goes above 15 volts. Automotive alternators output far more than 15 volts in cold weather. If you don't live in a cold climate, you probably haven't realized that, but they can go well over 15 volts when it's very cold outside. That's because they're temperature compensated, usually with a Zener resistor inside the voltage regulator. So if it shuts down at 15 volts, a lot of times it's rather useless in cold weather. This one doesn't do that. I like seeing that. These two outlets, by the way, do feel to be very good quality, really. They grab the plug very well. So these are perfectly adequate.